Okay, so now let's move on to this last problem I want to talk today. That is on finding a majority element. I mean, one can say maybe this whole algorithms for big data or streaming algorithms was born. This is one of the first algorithms in this world. So, what is a majority element, right? So, by definition, an element that appears, so it's not distinct elements. Okay, so you have a list of n elements. Not all are distinct, elements are repeated. And I want to know whether there is some element that occurs strictly more than half the times. The frequency of the element is more than n by 2. Okay. First question, does every list have a majority element? Need not be, right? If all elements are distinct, there is no majority element. Okay. Because I really want strictly more than n by 2. So how do I find this? Okay. So this is the, for now, let's say no constraints, no space, no access constraints. Just give me some algorithm to do it. So how do you find the unique elements first?
Whenever we come across a new element, we put it inside an array, and then the next time it comes, we check whether that element is already in the array, and then we increment the counter variable.
How much space will it take? Number of unique elements. Okay, that's an algorithm. I did say there are no constraints, so it's a fair, correct algorithm. So what she says is, I look at an element and I create some sort of a hash table, right? And every time I find an element, first check whether it has already appeared. I have to look at and hash it and put it in the table. That takes some time also. I have to scan and see whether it has already appeared. If it has already appeared, I'll increment the counter. If not, I create a new value and add it. Okay, so that's like n square with a lot of space. Why bother all that? Can you not do faster? Hmm? Hmm. Okay. Okay. So exactly, right? So I can say basically I check whether every element I check whether it's a majority element. How do I do? I compare it with everybody and there is a counter which tells you how many times it appears, and when the counter becomes more than n by 2, I know it's a majority element. So that's again n square time, but with very little space. Constant space is fine. Right? By the way, can you have more than one majority element? Right? You may not have majority element at all, but if there is one, it will be only one. Okay. Okay, so there is an n square element, constant space. Okay, no constraints I said. So can you do better? I want to beat n square because that's the current champion now. Let's see. What have we sought?
So if we sort, there's a probability it's either the lowest, median, or the highest, one of the three.
I don't want to get into probability yet. We'll wait for the afternoon. Probability is very confusing. Probability over what and all that. Okay. So let's stick to. So what happens if I sort? What then? Can you not find if there is a majority element? Yeah. How do I do after I sort?
Once we sort, if it would be at the minimum, the frequency would be, the element would be in the same order. Right?
Yeah. So all the repeated elements are appearing together, right? So I do one scan, that's all. So finish the sort, n log n time, and then take the first element in the sorted order, count its frequency, right? As I just go along, I found, how many times it repeats. I have a number counter, and if it's not more than n by 2, I can dismiss and move to the next element, and so that's like a linear time after that.
So again, then we have to manage the space.
Why? What space do you need?
Because if we do more sort.
So sorting. Okay, good question. Let's say we do heap sort, which is very good on space. Okay, we have an n log n algorithm. Bidding. Can you do better? Again, let's say no constraints on space or access. Okay, so we started with n square, a lot of space, n square with very little space. Now we have an n log n algorithm. Yeah, and I told you can find the median in linear time. Okay, so suppose I find the median element.
We can do binary search.
Binary search. No. Let's say I find the median element, right? Median element is the element which will occupy the middle element in the sorted array. And I told you using divide and conquer, you can actually find the median in linear time. Now, linear time, right? Better than n log n. Now, does it help you to find the majority element? So suppose your list has majority, okay? Suppose there is a majority element. Then what will be occupying the n by 2th position? If there is a majority, it is median. If there is a majority at all. There may not be a majority at all. Because if there is a majority, it appears more than n by 2 times. So it's going to, touch n by 2th position and go on. So suppose I manage to find the median. Now, what do you do?
We just iterate over the array once. Check if that number exists for more than n by 2.
That frequency of the median you found. Do one more time and you can check what is the frequency. So you found the median linear time, some clever divide and conquer algorithm. Take the median element, it may or may not be majority. Run through the whole list, checking the frequency of this particular element. You can do it in linear time. And if it's more than n by 2, because otherwise majority does not exist, because if the majority exists, median must be the majority. Okay, good. We started with n square with a lot of space, n square with small space, n log n. Now we have a linear time algorithm. Okay. Now I'm going to tell you a very clever, very simple linear time algorithm. Okay, so let me write down the linear time algorithm. Find median element, so that's order n, and check its frequency. It's a very clever algorithm which is attributed to Mishra-Grease. If you Google out, you will see Mishra-Grease some million times because it's just very simple, well-cited algorithm. Okay, so I'm going to demonstrate it. So let's say x is equal to a1, a0. So remember, your list is given in the form of an array, and I take the first element and store it. So for I going from 1 to n minus 1, okay, so let's also say counter is equal to 1. If ai equal to x, c is incremented, else it's much simpler to write in English than the code, but let me try. Okay. So if c equal to 0, maybe yeah, if C is not equal to 0, okay, maybe I'll do it in English, then we'll come back to it. Okay, so and maybe I'll do it in an example. Okay. Okay, so that's the list. Is there a majority here? Okay. Maybe you'll add one more. Now, still no? Yeah. Strictly greater than n by 2 times, remember. So it's not there, right? So let me. Okay. Okay, so I'm going to just scan this list and do something, okay? Store one value and a counter. That's all I'm going to do. So I'm here. So I will store this one value 7 and a counter which is 1. And as I see these things, this counter gets increased to 3. And once I see 6, counter gets decreased to 2. The 7 remains. Then I see 7, counter gets increased to 3. And then I see 2, 5, 3. So counter gets decreased to 0. At this point, okay, counter is 0. Do you understand what I did so far? Whenever I see an element which is equal to x, I increment the counter, and if it's not equal to x, I decrement the counter. Now the counter has become 0. I'm going to throw this element out now. Okay, so now 4 comes. So this is going to be thrown out, and now 4 is going to occupy because counter has become 0. 4 is going to occupy with the counter 1. Okay, and then next I see 4, so counter gets incremented to 2, and then I see 2 7s, which will actually decrease the counter to 0. Right, so I'm at this point. Counter has become 0. So now I have to throw this out 4. So I bring in 6 with the counter of 1. And then comes 7, which will kill this to 0. And the next 2 7, so I'm going to have 7 with the counter of 2. Okay, is that clear? Should I go over it again? Somebody said yes. Okay, so the algorithm is just scan the list. I store one element, first element start with. Whenever I see an element which is equal to this, I keep incrementing this counter as long as it's not 0. And then when I see if it's and when I see an element which is not equal to, I decrement this. When this has become 0, this is thrown out. The next element will go and occupy this place with the counter of 1, and I keep doing this. Okay. Now the claim is whatever survives at the end may or may not be majority, but is the only candidate for majority. Okay, so let's do one more. So I need to prove this. Okay, I will prove it. So now what do I mean? So first of all, the linear time algorithm we came up with is like find the median, which is a heavy duty, complicated divide and conquer algorithm. Okay, what I told you before. But this algorithm is fairly simple, right? Just absolutely simple. One pass, just uses one space. And I will prove this claim, but if I prove the claim, all I have said is this is a candidate for majority. Now to confirm it, what should I do? How do I do it? take that element and do one more pass over the input and count how many times it occurs, if it's greater than n by 2 or not. That's all. So linear time again with small space, and it's fairly low linear time, simple linear time, right? So in this case, 7 is the majority, but let's give you an example where it may not be, right? So let's do another example. Okay, I'll come back to this proof. Yeah, so let's give another example where it may not be, right? So let's take a simple example of okay, so suppose this is my list, okay? Let's follow the algorithm. So tell me what is X and C, right? So I have a 6 with a counter of 1. I see a 4, so it becomes 0. So now 0, so I'll throw it out and start with the 6 again with the counter of 1. And then 4 will make it 0. Then I start with 2, the counter of 1. 3 will make it 0. And then I have 1. 1 is far from majority, it just has frequency 1. Okay? So it may not be majority. That's why I said it is the only possible candidate for majority. Okay? So you need to do one more pass to check the frequency. So let's try and prove this. It has a fairly easy proof. So all I want to say is that every other element is not possible, its frequency is less than n by 2. Okay? They cannot be majority. Every other element has frequency less than n by 2. Okay, so let me just give you an intuitive proof, right? So every other element, they were knocked out of this counter, they became 0. And how did that happen? Because some other element which is not equal to this came and knocked it out. So if this appeared 3 times, then some 3 other guys maybe, or maybe the same element 3 times knocked it out. So I can do some pairing. So every other element which got 0, I can pair it with an element which is not equal to this. So for every occurrence of that element, there is another occurrence of an element which is not equal to it. That's it. So it cannot have appeared more than n by 2 times, because for every occurrence of this element, there is some other element which is not equal to it. So its frequency cannot be strictly more than n by 2. At best, it can be only n by 2. Okay, that's all the argument. You can formalize it. So, the only last surviving element is the candidate for majority. Okay, it's a nice clean algorithm. This is, it has its origin. It was reinvented several times in the years 70s, 80s. This was discovered Boyer and Moore, and then different people picked it up. But Mishra-Gries observed that it's sort of a streaming algorithm. So it's nice thing that I just need to do 2 passes over the input, and with constant space, I can manage to do this. Okay. Now, slight generalization of this problem, and it's even very interesting. Okay, so maybe I'll write this for every other element each of its occurrence can be paired with another element not equal to it. Right? Because every other element, how did it get out of this counter which I am storing? Because somebody else knocked it off. Its frequency went on, and then somebody else knocked off and became 0. So how did that happen? Because you think of it as like pairing this. So it cannot have appeared more than n by 2 times. Okay, so now there is a generalization of this, which is what we will look at, which is called finding frequent elements. Actually, that's what actually Mishra Gray's work is. Some find elements that appear greater than n by k times. Okay, these are actually important applications, like, majority you can imagine, right? Voting system, there is a sequence of votes and I want to find whether there is who is the majority winner and things like that. So similarly here, in this large stream of elements, given some k, let's say k is 10, I want to know which are the elements that have appeared more than n by 10 times. Okay. For some k, how many, more than n by k times. So if you want to do something naively, then it's very similar to what the algorithm you said. You need to keep some sort of a table, count the frequency of every element and see which has appeared more than so many times, lot of space and so on and so forth. But this majority algorithm can be generalized as follows. To solve this, again, very simple algorithm, like 2 passes over the input. And you will see this algorithm again and again in the later part of the course, improving space and so on. We are going to maintain a list of k elements with a counter for each. List of up to k elements, not always. Okay, so let's say it's some x1, x2, xk, and c1, c2, ck. Some of these positions may be empty, okay, because you may not be storing k elements, you may be storing some small number of elements. Right, so the algorithm goes like this. When I see a new element, what should I do? So we initialize it somehow, maybe start with x1 and c1 and then we'll apply this algorithm. When a new element y comes, is y is equal to xi for some I, then my ci will be incremented. Else, if the list has only less than k elements, add y to the list with the counter value, 1, And if the list, this is the interesting thing, if the list at any point has k values, decrement all the counters delete elements with counter value 0. Okay, so it's very similar to that majority algorithm. for this generalization. So I maintain k values and keep k counters. How many times they've come. I mean, may or may not exactly reflect how many times they've come, but some approximation of it. I take a new element. If it's not present here, I add it to my list. If there is space, because I'm allowed only k. Okay, there are only k allowed. So if I have only less than k elements, I add it to the list with a counter 1. If it is equal to any of the elements here, then I don't have to add, just increment the counter. If there is no space, new element is coming, that means there are exactly k distinct elements here. I decrement the counter, all the counters I decrement by 1, and I can argue that somebody would have become 0, I just throw that out. Anybody who has become 0, I throw them out and keep doing it. That's all the algorithm, and the claim is whatever is final surviving elements in this list are the only possible candidates for elements that appear greater than n by k times. So this is all the algorithm. Okay, this is the claim. So let's, in the next few minutes, let me demonstrate it on some example, prove this claim, and then we will discuss the time and space complexity of this algorithm. Okay, maybe time and space is easy to argue. So, by the way, algorithm is not over, right? Because I've just said these are the only possible candidates. So, what do I have to do? Just count the frequency of these k guys the next round. Okay, and then whoever is greater than n by q, output them. Okay, so let's do the time space first, and then I will prove this, and then we'll do the example. Okay, so how much time? Let's look at this, right? Yeah, so the first step, first step is to check whether y is equal to xi for some I. How fast can I do it? O of k, because I can just take the y and compare with each one. Can I do better by yeah, how do I, for that I need to maintain this elements in sorted array. But it has a problem. If I maintain it in a sorted array, I can check if y is equal to some xi, and I can maintain the counter appropriately, update the counter. If y is not equal to xi for any of the xi's and there is space, then I have to insert it. Okay, but in a sorted array, how much time does it take to insert it? O of n, right? So in this case it's k, so it will be order k. Can I maintain it in some other way so that the insertion is easier? If you use a linked list instead of an array, can I do this faster? How much time does it take to check whether y is equal to xi? Why not? What's the problem? k. But if I want to do it in log k, can I do binary search in a linked list? Why not? This is, revision of data. Huh? Yes, very good. This is a revision of your basic data structures thing. So, my question is, how do you maintain this sub list so that you can search? Because I want to know whether this y is equal to some xi, and if it's not equal to, then I also want to insert it. So, what data structure do I need to maintain so that I can insert and search in logarithmic time? Min heap, you can't search. Okay, there are many things you are learning in this 10 minutes. Okay, your quick revision of your data structures. Min heap doesn't work because you can't search for an element. A sorted array is not good enough because insertion takes order k time. Sorted linked list is not good enough because you can't do binary search. Binary search requires random access. You have to go to the middle element and then you are comparing. Middle element, you can't do it in a linked list easily, right? So, what do? AVL tree or some such balanced binary search tree. Okay. So, you all probably seen this data structure, the AVL tree. You've never thought about why do I need it, right? Because you never asked why, right? So, that's a data structure where you can insert and search in logarithmic time, and you need this heavy duty balanced thing because the simple things don't give you that efficient access and insert. Okay, so this is like order log k, not just this also, search and insert. But this is going to be a killer anyway, because if the list has k elements, then you're going to decrement all by 1. Maybe if you are clever, if you are a programmer competition person, you can do this in one step. Maybe you don't have to go to each counter and then decrement it, because you're doing it uniformly for all the counters. Maybe some other variable you keep track of, saying how much you have done in how much decrement you can do. Think about it, okay? But if I'm happy with even nk or n log k, so I'm going to just say that this time is like n log k. And the second confirmation phase, where you're going to take your k elements and count its frequency. Again, that's naively is going to take you some kn time, right? Because you're going to take this element and count its frequency. Or somehow you can take this k element, merge with, so I'm just going to leave this, maybe can be discussed in the tutorial. So, total time, let me put naively as order nk and say that with a question mark, but this is not going to be so much important for us. K is going to be 3 or 4, 5 in real world practice, because I want to know which are the elements that have appeared more than n by 10 times. So, k is small constant. So, and even nk I may be willing to live with, but it can be, as a good programming or algorithmic exercise, think about, can I do it in n log k time? But how much space? Space is going to be, k counters you are storing, right? So, that's k log n plus your k elements you are storing. But maybe that elements you don't have to store, you keep some pointers or something, but And we will see maybe in next 4 days that the space can be considerably improved to log n rather than log n or something using randomization. Okay, so that's the game we are going to play as we go along, is that using randomization, some of these bonds we come up with can be considerably improved. Okay. So now I'm going to just try and show the claim, this claim. Yes, I'm almost done. So it has a very similar flavor like how we argued that in that majority algorithm, the only surviving element is, and other elements have frequency less than n by k. Okay, so it will be like a 2-line proof. So one way to think about this. So let's again, maybe should I do it on an example? Yeah, let's do an example, right? So let's say k is 3, and I want elements. Okay, and let's. Okay. So I'm looking. So how many elements are there? N is 12. And n by k is 4. So elements that appear more than 4 times is what I'm looking for. Okay. So I will maintain 3 counters. So it will be 7, 6, 3 with a counter value of 1, 1, 1. Okay. So the number of elements is 3. So at this point I have to do something. I don't want to make it. So what do I do? Remember what I was doing when I reached the full list? Decrement all elements by 1, because that was out, right? If the list has k elements, I will decrement. So here it is, right? The list has k elements, I'll decrement all the k counters and delete all elements with counter value 0. So all of this will become 0, 0, 0, and they're gone. Then I look at 6, 7 with counter value. So I look, when I read C6, I will have counter value 1. When I see 7, it has counter value 1. The other 7 will make it 2, the other 7 will make it 3, and the other 7 will make it 4. That 6 will make it 2. Then I have 2 with counter value 1. So I'm here. So decrement everybody by 1. So this 2 will go away because it becomes 0. So this will become 1, this will become 3. Now 3 comes with the counter value of 1. Now counter is full, so decrement all of this. So this will go away as 0, this will go away, and 7 is the one which survives. 1 will come with the counter value of 1. And the claim is that these two values, 7 and 1, are the only possible candidates. And then you verify the frequency. Okay, so let's do the proof of claim. Why is this? Some magical thing that happens, you're doing this, and finally the only thing that survives is the only possible candidate. So I will argue that whatever you have thrown away, their frequency cannot be strictly more than n by k. At best, their frequency can be equal to n by k, not more. Okay. So one way to think about it is that I am grouping my n elements into groups of size k. Okay, so think of it this way. So I have these elements and I have this k counters, which is formed or k sublist formed according to my rule. And when I decrement every element by 1, think of it as I am removing those k elements and forming a group. Okay. So, when I decrement this, I removed those k elements and formed a group. I mean, if somebody would have become 0, it doesn't matter. Think of it as everybody, one copy of every element is from the list is removed and put here. It's a separate group, right? So, as the algorithm proceeds, I am forming some groups of k elements, and the important thing about these k elements is they are all distinct, because this is k different things I have put it in my sublist. So, when I decrement, think of them as I am removing them and forming a group. I removed it, another group, removed them, formed a group, right? And then finally, some things survived. So, I have not yet removed because the list is over. Now, look at every element, every other element, right? Any other element which is not in this group. How many times can they have appeared, right? So, how many different groups are there at most? So, suppose there are n elements. How many different groups are there? N by k, because each group is of size k, right? Strictly, there are some more elements left. So, at best, the number of groups is n by k, right? And any element not in this final list can appear at most 1 in each group, because each group has all distinct elements. Okay, that's it, end of story, right? So, any element not in this final list can appear at most once in each of the groups. The number of groups is at most n by k. So, their frequency can at best be n by k, not strictly more. The only possible candidates here are the ones whose frequency is strictly more than n by k. Okay. So, any element not in final list can appear at most once in each of the that's it. So, this is again important practical problem. You want to find an element with very high frequency. Very simple algorithm. You are just doing one pass to identify some candidates, another pass to do some confirmation, and fairly fast algorithm. Simple algorithm, uses space, some k log n bits. Okay, and again, I mean, imagine for k equal to 2, which is a majority problem, the kind of algorithms we started off with, right? Our naive algorithms were very complicated, but sorting or finding median. But here it's just one pass, just do some little counters and that's it. Right? Majority algorithm was constant space, and here it constant number of variables. Here it's like k variables. Okay, I think that's all I want to say. So, in the coming days, we will revisit this problem again and carefully look at the space and improve it. Now, another question you can ask is, in this majority and frequent fitting algorithms, you are doing two passes over the input. One pass to identify the candidates, the other pass to confirm it. Suppose I don't have a luxury of two passes. I'm allowed only one pass. This is another sort of constraint one can build in this big data world, right? I'm allowed only one pass, then one can prove that whatever you found in the final list, which is an easy extension of whatever we have shown, is that the counter values that you have are pretty close to their actual frequencies. I mean, it's not because you've decremented a lot. That's why it's close to. Okay, so there is this approximation and randomization we will bring in to improve some of these, to meet some of these constraints on space or the number of passes. Okay, we'll get to those later. Okay.